Okay, good evening, everyone. Okay, wishing everybody a happy new year. Okay, hope you all had a good and enjoyable long weekend. All right, so let's get started. I think most students usually start coming in slowly after 6:30. So we will start off with reviewing where we stopped last, which is the jump instruction. Okay, and after that we will move on to the next chapter on the data path. All right, after data path there's one more chapter on control, and with that we will wrap up the entire MIPS portion of the module. Okay, uh, and after we are done with that, yeah, then probably next lesson we can do the tutorial, next tutorial as well. Okay, so let me share screen, and we can resume from where we left off. Okay, so the last lesson we were talking about the jump instruction. Okay, and for the jump instruction, we basically know that it's an unconditional jump, all right? Because when we say it is a jump instruction, we are not checking for any condition, unlike branch, where you say branch equal or branch is not equal. So for jump instructions, we will jump, okay, unconditionally. And the main thing that we were discussing is how do we specify the address to jump to. Okay, so you must remember that we are dealing with a 32-bit memory system. That means the address is also something that we have to specify in 32 bits. Okay, now how do we deal with this? All right, for every instruction in MIPS, we know that we already have 6 bits that are reserved for the opcode. Okay, since 6 bits are reserved for the opcode, we are only left with 26 bits. Okay, and how do I make use of this 26 bits to translate it into a final 32-bit address? Okay, so that is what we were discussing last. Okay, so the manner in which it works is, firstly, we know that all our addresses are word aligned. All right, and since they are word aligned addresses, that means it always has to, the last 2 bits always has to be 0, 0, okay, in terms of binary. So if you look at this sequence that we did, okay, if I were to do a counting 0, 1, 2, 3, then 4, 5, 6, 7, and so on, you can see that the last 2 bits will be 0 whenever I start on a word boundary. Okay, this is 4 bytes, and then 4 bytes, and so on. Okay, so whenever I start on a word boundary, the last 2 bits will always be 0. Okay, so with that, we can now say that the 26 bits automatically becomes 28 bits, because we can now ensure that the last 2 bits will always be 0, since you're always going to jump to a word aligned address. So how about the remaining 4 bits? The remaining 4 bits is taken from the PC plus 4. Okay, so if you recall, whenever I fetch an instruction, my PC automatically increments by 4 to point to the next instruction. Okay, so I can take that PC plus 4 and then pad it with the current 28 bits, and then I'll get my full 32 bits. Okay, so that gives me the 256 megabyte range. Okay, so if you do 2 to the power of 28, okay, you will get 256 megabytes. Okay, of course, this is in most cases more than enough, all right, for instructions in our code. Okay, but in situations where your jump address is beyond this, okay, then your compiler may again use some other instructions. Okay, and one of it is what we call a JR instruction, where we jump. Okay, but when we jump, we specify the address in the register. Okay, but this is not something we are going to cover. All right, but this is just for information only. Okay, what we want to know is, as long as we know how to interpret the jump instruction using this format, then that is good enough. All right, So this is the example we looked at. Okay, so if I give you this jump instruction, if I tell you this is a jump instruction, okay, so of course, how do you know it's a jump instruction? We look at the output. Okay, so let's switch to the data sheet. Okay, so if we look at the jump instruction over here, okay, this jump instruction, you can see that the opcode is 2. Okay, it is 2. So do take note that all the opcodes here are in hexadecimal format. So you see the small hex written there. Okay, so in our notes, sometimes we will refer to them in hexadecimal form. Sometimes we will just refer to them in decimal form. All right, but as long as you know what representation you're using, then it's fine. Okay, so for jump instruction, the opcode is 2. Okay, so coming back here, we can see that this represents a value of 2, 0, 0, 0, 0, 1, 0. So that is the opcode. And since this is a jump instruction, the remaining 26 bits refers to the or we will use the remaining 26 bits to calculate the actual address to jump to. All right. So how do we do it? So firstly, we know that the PC plus 4, which is the current PC plus 4 value, will be copied over. Okay, so we will retain that. The 26 bits over here is again directly copied over as well. Okay, and we also know that the last 2 bits will be 0. Okay, so now you see that I have a full 32-bit address that I am going to jump to when I execute this instruction over here. Okay, so this is the final address, okay, that I will jump to. Okay, now of course we can also work backwards, all right, by trying to look at the instruction, okay, that I would generate, okay, if I were to uh, execute a jump instruction. Okay, so let's look at this example. So in this example, I am currently, my current PC is here, okay, over here, and I'm going to execute an instruction called J loop, that means jump to loop. So loop is, the label is over here. All right, so this address is given as address 8. Okay, so address 8. So how do I go about doing it? So since this is my instruction, address, my PC is currently pointing to this 20. So this value here is value 20. Okay, PC plus 4 again is not going to change anything because plus 4 will only change the lower bits. All right, in this case, it's a very small number, so you can expect that the upper 4 bits will remain the same. All right, now the address I want to jump to is address 8. This is the address I want to jump to. Okay, so if I were to write out the full address, it will be all zeros, and then the last 4 bits will be 1, 0, 0, 0. Okay, so this is the address that I want to jump to. So I need to now, so this address is 32 bits, correct? And from this 32 bits, I need to extract out 26 bits. Correct? I need to extract out 26 bits. And how I extract out 26 bits is I remove the last 2 bits, correct? Because that is always going to be 0. And I also remove the upper 4 bits because that is the PC plus 4, which is going to be retained. So whatever is remaining is the one that is actually going to be encoded as part of the jump instruction. Okay, so that is what you see over here. What you see here, okay, is actually what you see here. The last 3 bits are 0, 1, 0. Okay, so of course, this is the encoding part. So if you look at it from the processor perspective, when the processor fetches this instruction, when it fetches this instruction, what will it do? It will look at the first 6 bits, it will know it is a jump instruction, then it will take the 26 bits from here, okay, and then it will work backwards. That means from the 26 bits, it will add 2 zeros behind, Okay, and then it will take the current PC plus 4 value and put it in front, and then it will generate the full 32 bits address that is going to jump to. Okay, so you can see that in either way we can relate the process quite easily. Okay, so of course this is just another thing to consider. For branch instructions, we say that it is supported, okay, up to a limit. Yeah, so this is the slide. So it's to the power of plus minus to the power of 15 locations from the PC. Okay, so so this is the limit I'm talking about, where you say that you have a upper and lower limit for this label. All right, so anywhere within this range you can cover. Okay, but what if it's beyond the range? Then if it's beyond the range, okay, so that is what we are talking about. Okay, so if it's beyond the range, then uh, from the compiler's perspective, if it sees that this label is beyond the range, it will reconstruct, okay, some additional code to branch to somewhere else and then do a jump, okay, depending on what is the final location. Okay, so for example, since it's already a branch instruction, okay, it may choose to branch to some other location that is within this range, okay, somewhere here or here, and then from there I can do another jump, okay, to the actual location that I want to go to. Okay, again, these are things that the compiler will automatically do for us, okay, if that label is beyond the range that is supported by the instruction. Okay, so that basically sums up the jump instruction. So this is just to give you a quick review of the different addressing modes that we saw: the register addressing, immediate addressing. All right, so I think what is important here is for immediate addressing, okay, register addressing I think is quite clear. All three of them are registers, correct? Two source registers, one destination register. For immediate addressing, we have two registers and one immediate value. Okay, and if you look at in terms of addressing for memory location or memory access, it is also the same format: two registers and a 16-bit value. But the main difference is over here we are performing an operation on the data, all right, directly and together with the immediate value, and that is a data operation. That result is again stored back within the register itself. Whereas in memory access instructions, okay, the operation we're carrying out is actually to point to some memory location, to point to an address in the memory. Okay, so that is the uh, main difference here. Okay, so the load mode and store mode instructions, we are performing a arithmetic operation to know the eventual address that you're pointing to. Okay, and from there we either take that data or store data into that location. Okay, so that is the addressing mode, similar to BEQ and BNE as well. The same concept applies. All right, where you are checking for some equal or not equal comparison, and then using that result to branch to a particular address. All right, and the address is also specified as the eventual address using the current PC value and the offset specified in the instruction. All right, for the jump instruction, we are again jumping to a memory location which is specified together with PC plus 4, and then the 26-bit address inside your instruction. Okay, so that basically sums up all the main sort of modes of operation, okay, for your processor. Okay, so now the next lecture we're going to go to is the one on the data part. Okay, so let's move on to the data part lecture slides. Okay, lecture 7. Okay, so In lecture 7 here, what we are going to be looking at is a very important part of the whole processor design, which is, okay, now we understand what each instruction is supposed to do, correct? If I have an add instruction which is R type, I know that I have two registers, take the data, add and put somewhere in another register. If it's a load memory, I know I'm now supposed to take the contents from a memory location specified by a register and for and a immediate offset, and take that content and put it into a register. So we know that these are the instructions. We know what these instructions are supposed to do. Now the important thing is when the processor fetches this instruction, okay, how does it go ahead with executing these operations for us? Okay, so that is where the data part and control lecture come in. Okay, so first we're going to be looking at the data part, okay, and then following that will be the control. Okay, so these are two very interlinked blocks. Okay, we will actually be covering some of the control elements in this lecture as well. All right, so that you have an idea on what is happening. All right, so let's go ahead to build up our own MIPS processor. Okay, with the understanding of how the instructions or what the instructions are supposed to do for us, and then how we are going to encode these instructions and make the processor perform the necessary operations. Okay, so these are some of the instructions we have already seen: the arithmetic and logical operations, the data transfer instructions, as well as branches. Okay, so some instructions we will not discuss in the lecture. All right, but we will just have a look at it later on. All right, possibly in the tutorial. Okay, but if it's not covered, then it's fine. All right, as long as you understand the concept of what is happening when an instruction is going through the processor, then you can relate it to a lot of other instructions later on as well. Okay, so in terms of the sequence of operations, we can sort of break it down into these 5 steps. Okay, so the first step is fetch the instruction from memory. So when you say fetch the instruction from memory means, okay, so for example, if I say add, okay, S0, S1, S2, correct? So I fetch this instruction from memory. Okay, of course, this memory, where is it in memory, is already specified by my program counter register. So after I fetch this instruction from memory, I need to decode. Okay, so when I do a decode means what? That means I need to know that, okay, I am supposed to do a add operation here. All right. Now the next thing is operand fetch. So operand fetch means get the data I'm supposed to deal with. All right. So in this case, S1 and S2 are my two source operands. Okay. If it was a memory operation, then I may need to fetch some data from one of the register, then take the immediate value and so on. Okay. So it depends on the type of instruction you're dealing with. Is it R type? Is it I type? And so on. You fetch the or you get the data ready. Okay, the data that you need to perform the operation on. Once the data in S1 and S2 is ready, in this case, I can perform the execution. That means I perform the add operation. Okay, once the data is ready. And once the result is available, I must be able to write back into the final destination register. Okay, so these are all the different stages your processor must be able to go through, okay, in order for us to successfully execute this instruction and get the desired result. Okay, now let's look at these three different type instructions. One is the R type. Okay, one is R type. Okay, this is I type. This is also I type. Okay, of course these are different. Okay, one is I type with memory access. This one is I type, okay, with the branch operation. Okay, so it is different type of instruction. Okay, but what we want to look at is where is the data, what kind of operations am I doing over here. So if you look at these three instructions, of course I need to fetch and decode. That is standard operation every instruction has to go through. Okay, then for the R type, you can see that I fetching from registers, whereas here I take from one register and I take the immediate. Correct. But in this instruction, okay, you can see that even though both are I type, both are considered I type instructions. Okay, the BEQ instructions are actually read from both register 1 and register 2. Okay, so the the data, where the data comes from, okay, for me to perform the operation is different. Okay, even though they are both classified as I type instructions. In this case, again, the execute is also different because in this R type instruction, I am performing a add operation, okay, and then I will write back the result later on to the register. In the I type instruction over here for the load word, I perform the add operation between the data in the register and the immediate value and use that to read from memory. Okay, and then the data that is in the memory is the one that is eventually returned back to the register. Okay, and in the last instruction over here, I am actually just doing a operation of comparison between two sets of data, and based on that result, I will decide whether to take the branch or not. Okay, so in this BEQ, I'm not writing to any register. I'm not updating any register. Correct? Register 1, register 2, both will not change after the operation. I am just going to make use of the result of whether they are equal or not to change my PC value. Okay, so three different types of instructions, okay, doing very different things. Okay, but your processor must be able to interpret each instruction correctly and perform the necessary steps for us. Okay. Okay, so this is slightly further just readjustment of what we're trying to look at, okay, in more detailed steps. So if you look at it, the first fetch instruction, yes, every instruction we have to go to the fetch. In the second, decode and operand fetch is where you can see that in different instructions, I read the data from different locations or use the data from different locations. The operation again depends on what is the instruction I'm executing. Is it an add? If it's a load word or stalwart, it will still be an add, okay, because I am actually performing the operation of performing the addition of the offset or the displacement with the base pointer, which is the register value. Okay, in the branch instructions here, I'm doing a comparison, okay, to check whether they're equal or not. Okay, in terms of memory access, okay, only the load word or store word instructions will have a memory access. Okay, the other instructions over here, both add and BQ, don't have any memory access, but we are just going to either update the register or change the PC value. Okay, and the last stage here, you can see that all three are different. Okay, one is write back to a register, one is to take the data from the register, from the memory and update the register, and the last one is to change the PC value. Okay, so these are the different type of instructions. Now let's go through each stage, okay, step by step, and try to understand what is happening. Okay, so the first stage is what you call the instruction fetch stage. Okay, where you are fetching from the memory. Okay, and that information on where to fetch the instruction from, that is inside this register called the program counter. Okay, so in this this register program counter basically points to where I want to fetch the instruction from. All right. And the moment I fetch one instruction and I send it into the system or to the processor to start executing, I'll automatically increment to PC plus 4. Okay, why? Because every instruction is one word. Okay, 4 bytes long, so I automatically increment by 4. Okay, so that is basically the objective of the fetch operation or the fetch stage. And once the instruction is fetched, it will automatically go to the next stage, which is the decoding stage. Okay. So let's look at the fetch, uh, the way the block diagram is designed. All right, so this is the instruction memory. Instruction memory is the place where instructions are stored. The program counter, you can think of it as just another register, just like how we use the S0, S1, A0, A1 registers, okay, to hold data for us, to hold information for us. The program counter is also another register, but in this case, the information that is stored is always the address of the next instruction to be executed. Okay, and what comes out, okay, is the instruction, which will then go on to the next stage. And here you see an adder block. So this is what we call a hardware adder. Okay, so a hardware adder is just like a block that performs the operation automatically and gives us the output. Okay, so whatever value that is over here, which is the current PC value, I will automatically generate a PC plus 4 and feed it back over here. Okay, to the input of the program counter register. Okay, so those are the three main blocks over here. Now, the important thing is the idea that everything is sequential in nature. Okay, that means there is actually what we call a clocking mechanism in place. Okay, so even though we are not going into the details of the clocking mechanism, all right, every processor has to have a clock, okay, in order to start to execute instructions and process the data. Okay, so the whole idea is when the clock comes in, then I can go from the current stage to the next stage and so on. So that allows you to transition from one state to the next state and carry on. Okay, so in terms of the memory, instruction memory, what is inside the memory? Okay, what is inside the memory is instructions. Okay, that's why we call it the instruction memory. And every instruction is one word long. That means 4 bytes. Okay, so every instruction is 4 bytes. Wherever I'm fetching from, the next instruction will always be 4 bytes away, 4 bytes away, and so on. Okay, so that is how your address will look like. It'll always be one word away, 4 bytes away. All right. So the adder block is nothing more than a simple adder. So you think of it as just adding two numbers together, all right, and giving us another 32-bit output. Okay, so the adder is quite straightforward. Now, let's come to the idea of the clock again. All right. So in order for us to make sure that the system can work properly, okay, we have the clock that ensures that when the active edge of the clock comes in, the data is updated and the new instruction is fetched. Okay, so over here you can see that the okay, let's look at this clock diagram. So if currently my program counter has a value of 100, that means I'm here, that means 100 was the data that was last pushed out from the PC to the instruction memory. Okay, so when that happens, all right, I will automatically generate 104 through the adder and standby 104 at the input of the program counter. Okay, and when the clock comes in, so in this case the positive transition of the clock comes in, what happens automatically is the next state automatically is triggered. That means the program counter will take the value that is at the input and transition it to go to the output. Okay, that means 104 will come in. So from 100, I'll become 104. Okay, so 104 comes in means the instruction at address location 104 will then be channeled out of the memory to the next stage of the processor. And when 104 comes in, I will add 4 and I will generate 108, which will now come in and stand by over here. Okay, so that is why you see when my program counter is at 104, 108 is already at the input side of the program counter. Okay, but it will not get updated until the next edge of the clock comes in. Okay, so that is the what you call the magic of the clock. Okay, so every time a clock comes in, okay, I will be able to transition automatically to PC plus 4. All right, so this is basically how the hardware, okay, of the processor is designed to ensure you are always going to the next instruction sequentially. Okay, so of course, as we have seen, there are branch instructions, there are jump instructions, and so on. So later on, we will look at how we need to make some modifications to accommodate those type of instructions where the PC will change. All right, but if there is no change, by default, it will automatically go from PC to PC plus 4. Okay, so now we have completed the first stage. So this is done already. And now we are at the decode stage. So what do we do in the decode stage? In the decode stage, we want to get two things. Firstly, we want to read the opcode. Okay, we want to read the opcode to know exactly what we need to do. All right, because the most significant 6 bits are the opcode of your instruction, and that will tell your processor what type of instruction we're going to deal with. Is it a add instruction? Is it a R type? Is it I type? And so on. Okay, and at the same time, once we have the information, we will also be able to know, okay, where to read from in terms of the registers. So when you fetch the instruction, we are getting the opcode, plus we are also getting the information on the registers I need to access data from. Or in some cases, your instruction is also holding the immediate value. Okay, so I need to also use the immediate value for some calculation. All right, and once I have all this information ready, then I can go on to the next stage, which is the ALU stage. All right, so let's look at the decode stage again. Now for the decode stage, as we have seen, the instructions that we deal with, okay, in almost all cases involve register access, correct? All right, except for jump instruction. Jump is the instruction where you don't need to read any register value. You can directly take the instruction and just adjust the PC value to go to a new particular address location. But all other all other instructions do require you to access the data in registers. Okay, so if I were to say add, okay, S0, S1, S2, okay, or load word into T0 for T1, something like that. Okay, so all of these type of instructions will require me to have register access. So that is where the register file comes in. Okay, so we'll talk about register file in a while, and then the data from the register file will then be passed on to the ALU stage. Okay, so the register file is basically a collection of all the registers that we have. Okay, so let's look at the register file in a bit more detail. So we know that our MIPS processor has 32 registers. Okay, so if you just go back to your data sheet, okay, you can see that all the registers are specified here. Okay, so from 0 to 31, right, total of 32 registers that we have in our MIPS processor. Okay, in your code, you can either use the numbers or you can use the name. Either way, it is the same. Okay, so that is for your 32 registers. So inside your MIPS processor, I must be able to access all these 32 registers. So that is where this register file comes in. So it's just a collection of all the 32 registers. Okay, so you can imagine that I have a total of 32 registers. So this is register 0, 1, 2, all the way to 31. And each register is also 32-bit wide. That means inside each register here is actually also 32 bits. Okay, so 32 registers and each register is 32-bit wide. All right. So for some instructions, I may need to read one register or at most two registers, depending on the type of instructions. And when it comes to writing, I will also be required to write, but at most I write only one register per instruction. Okay, so these are some of the things we have seen in our instructions so far. Okay, if it's R type of instructions, I read at most 2 registers. If not, I read 1 register. When it comes to writing, I will only write back to at most 1 register. There is no instruction where I'm required to write to 2 registers at the same time. No. Okay, so these are some of the uh, behavior of the MIPS that we have seen, okay, from our instructions. Okay, so that is where, okay, the design of the register file comes in, where you can see that I specify 2 ports to do the read. Okay, so this here, this line here, 5 with a slash. Okay, so this tells us that this is a 5-bit line. Why 5 bits? Because 2 to the power of 5 is 32. All right, so by specifying the 5 bits here, I am telling the register file where or what data I want coming out of this read data one. Okay, so for example, okay, if let's say the data over here in read register 1, this 5 bits is 00101. Okay, 00101 is value of 5. Okay, value 5. That means I want to go to register 5, take the data in register 5 and put it out to read data 1, RD1 here. Okay, similarly, if I specify a value here in these 5 bits as 00001, which is value 1, then I'm saying that I want to go to register 1, take the 32 bits and put it out into the port which is read data 2. Okay, so that is how the 5 bits for read register 1 and read register 2 is interpreted. Okay, now there's also the need for us to, in some cases, update a register. Correct. So if I were to have an instruction that, for example, says add, okay, S1, T0, and T1, I know that in the end I must update register S1. Okay, so I need to specify the register that I want to write in these 5 bits over here. That is the write register. And I also need to tell the register file that I need to do a write operation after I finish everything. Okay, so that is where the control signal comes in. So one of the control signals, okay, is this pin called the register write. So this control signal tells this block here that when I finish everything, okay, I will be required to perform a write operation to one of the registers. Okay, the register is specified over here. Okay, the register is specified over here, and the data will come here. Okay, we will see how the data is channeled back over here later on when we complete the whole data part. All right, but we know that I need to write back later on. Okay, but when I fetch the instruction, I already know the register I want to write back to, correct? Because I already know that in this case I want to write back to register S1. But what I do not know is the data, because the data is not ready yet. Now only I am reading the data for the 2 registers, correct? That data is going to come out over here and over here. Okay, later, after that, I must do the addition. After all the addition is done, then only the data is ready for me to write back. Okay, so we will see that later on. Okay, but you can see that the register file is designed so that we are able to access the data from the registers and pass it on to the next stage. And at the same time, in cases where I need to do a write operation, I can also specify which register that I'm going to write to. Okay, so that is the register file. So let's look at it, okay, with this example here. So in this example, we have this instruction called add 8, 9, 10. Okay, so I'm going to take the data from register 9. Okay, they take the data from register 9, take the data from register 10, do a add operation, okay, and then take the result and put it back into register 8. Okay, so the first thing that we must know is the instruction encoding. Okay, so the instruction encoding is what we covered in the last lecture. So firstly, the add operation. So this is the R-type instruction. This is R-type instruction. So for R-type instruction, we can look at add. So for add, we can see that add, we can see that the output is 0 and the function field is hex 20. Okay, 0 and hex 20. Okay, so with that, we can put in that information here. So this is 0 and this is hex 20. Okay, and this is RS, RT, RD. So RS and RD. So this is your RS, this is your RT, this is your RD. Correct. So this is your 9, this is your 10, and this is 8. Okay, and for add instruction, shift amount is 0 because it's not used. Okay, so that is the first step, taking the instruction and translating it into the appropriate 32 bits. Okay, encoding. And once you have this encoding, okay, you can see why we are particular about arranging the order in a standard format all the time. Okay, why is always opcode over here, RS, RT, and so on. All right, so that you can see the link now. So what or how the processor is hardwired is it will automatically take the 32 bits. So this instruction here is 32 bits. For every instruction is 32 bits. But what I know is bits 25 to 21, okay, will specify RS, which is the register I want to read from. So this is register 9. Okay, bits 20 to 16 is RT, which is register 10, which is the second register I want to read from. And then finally the RD, which is the destination register, is 8, which is the register I want to write back to. Okay, so I can straight away from the full 32 bits extract out bits 25 to 21 and connect them to read register 1, and 20 to 16 to read register 2, and 15 to 11 to write register. Okay, so I can hardwire this connection because I know that these bits, okay, from the 32-bit instruction that comes out of the memory, these bits specify the registers that I'm dealing with. Okay, so what happens once I put the value of 9 into these 5 bits of read register 1, what comes out is the content of register 9. Okay, so if you go back here, you can see what I drew. So when I specify a register number here, when I specify a register number here, what will happen is I will go and take the contents that is inside that register and put it out into the RD1 and RD2. So that is what is happening here. Okay, the contents of register 9 will come out over here on RD1, and the content of register 10 will come out over here in RD2. Okay, and we also know that I'm going to write back to register 8, so that is already specified over here. Okay, but the data to write back will come later only. Okay, the data will write back will come later. but we already know that we need to write back to register 8. Okay, so you can see that the reason why we do this particular format and uh, arrangement of the bits is so that it matches the hardware. Okay, so the hardware can be designed in a way that is always consistent, because we know that when we read the instruction, specific bits uh, relate to different registers or values and so on, which we can reuse. Okay, how about the I format? Okay, just give me a minute. Okay, so let's come back. So for the I format, okay, so right now what we have seen is the R format. Okay, and for the R format, the mapping and all is no problem, right? Everything falls in place very nicely. But now let's look at the other type of format, I format, and let's see what is going to happen. So for the first thing is we need to be able to translate that instruction to the correct encoding. So add I. So add I. Let's go back to our data sheet here. So add I. Okay, you can see that the opcode is 8. Is 8. There is no function field. Okay. For add immediate, so it's only opcode 8. So if we come back here, you can see that this represents a value of 8. All right, and this is your RS, and this is your RT. Okay, RS and your RT. Now for this instruction, you can see that your RS here is 22 here, and this is your 21. Okay, so now the immediate value of negative 50. Okay, the immediate value of negative 50 can be represented by this. Okay, so if you are not sure, again, you can always use your calculator. Okay, if you use your calculator and go into programmer mode, okay, so 50, you put a negative sign, you can look at the lower 16 bits. Okay, so you can see that this lower 16 bits matches this. Okay, of course, if you want to calculate it out manually, you can take 50 and then do the 2's complement, then you get the negative 50 over here. All right, so I'll not go through that, but this is basically representing negative 50. Okay, this 16 bits. Okay, now let's see what happens when I take the current hardwired mapping and apply it to I format. Okay, what happens? Okay, over here, the RS data, which is 22. So this RS, so this is 22 comes in. So the contents of register 22 come out. Okay, which is good, which is correct, because that's what I want. Okay, but what is the problem now? The problem here is for this add I instruction, the destination or the place where I'm supposed to store the result is actually this. Is actually RT, which is register 21. But RT, okay, because the encoding is such that it is in bits 20 to 60. Okay, RT is over here. And that is currently hardwired to read register 2. So the data from read register 2, which is contact 21, is going to come out here. Okay, but that is not what I want, because I'm supposed to do the addition operation. Okay, I'm supposed to do the addition operation and store back the result into register 21. So there is a problem here, correct? So how do we go about this? Okay, so the way we can go about this is we need to provide what we call a multiplexer. Okay, so what is a, let me go to this first, multiplexer, and come back here. So what is a multiplexer? Multiplexer, okay, you can think of it simply put as like how you use your TV at home, correct? When you switch on your TV, you can select, okay, you want to watch your Starhub or Singtel, you want to switch to Netflix, you want to switch to YouTube, okay, you can switch to many possible input channels. So these are all the possible input channels, but everything comes out on one TV screen, correct? Okay, so on one TV screen, you see it, but you can decide what you want to see. All right, and you can switch between any of them. So that is the easiest way to understand multiplexer. And then you have a control. Okay, so like just like how you use a remote control, you have a way to select, okay, which of the inputs you want to channel to the output. Okay, so the idea is the input and output all have the same set of data weight. Okay, that means if here I have 8 bits, each of it is 8 bits, then the output also might be 8 bit. All right, now the control depends on how many input options I have. Okay, how many input options I have. That means if I have 3 bits over here, that means I can specify 2 to the power of 3, which is 8 possible options here. If I have 4 bits over here, then it becomes 2 to the power of 4, which is 16 possible inputs over here. Okay, so the control bits will tell me how many different inputs I can have, and out of that, I will select one of it to be channeled to the output. Okay, so that is the idea of a multiplexer. So now let's come back over here. So now what I'm doing is I'm adding a multiplexer over here. Okay, and what does this multiplexer do? It takes in the bits 20 to 16, okay, and 15 to 11, and then one of it will be channeled to be the right register selection. Okay, so now I am now providing more variation to how the processor is going to behave. When we first started off with the R type, we say everything just hard code or hardwire, right? RS, RT, RD, all hardwire. All right, and it works if it's only going to be R type. But the moment you have a slight variation, okay, then you need to take into account how the data will now move around. Okay, and the way data is channeled to different parts of the processor is actually through this kind of multiplexers. Okay, so now using this multiplexer, I can decide whether the right register is specified by the bits in 20 to 16 or by the bits in 15 to 11. If it was a R type, it would have been this selection. If it is I type, it would have been this selection, 20 to 16. Okay, so you can see that the multiplexer will help us decide. And now with the introduction of the multiplexer, we have another control signal, which is the register destination. Okay, so early on we saw the first control signal, which was register write. Now we have a second control signal, which is the register destination. Okay, so your question. Okay, so why can't we read the immediate value as read data 1? Okay, because if I channel this immediate data here, all right, then how do you differentiate between I mean, if you channel this these 5 bits directly over here, the problem is for a I type instructions, these 5 bits don't specify the register. The 5 bits that represent the register is here. Okay, it's over here. Okay, okay, it's specified here. So if I take the 5 bits from the immediate value and I put in here, but those 5 bits of this immediate value are not actually specifying the register. They are actually part of the immediate value over here. Okay, so for the I-type instruction, the destination register or the register that is supposed to store the result is specified by bits 20 to 16. Okay, so when I say instruction 25 to 21, okay, that means it is telling us the bits. Okay, so for example, this 20 to 16 means I'm talking about the bits 20 to 16 from the instruction. Okay, so the instruction is 32 bits, correct? But we already know that different bits represent different parts of an instruction, and also it depends on the type of instruction you're dealing with. Okay, so as you can see previously, okay, so if I go back to the R type, okay, so for the R type instruction, everything falls in place very nicely because the bits 25 to 21 is one of the register I want to read. So it maps directly to read register 1. Bits 20 to 16 is the other register I want to read. So it maps directly to read register 2. And the bit 15 to 11 is the register I want to write back to. So it also maps directly to the write register. Okay, so this sort of hardwired connections will work perfectly well as long as it's only R type instruction. Okay, but when I move over to I type instruction, okay, the challenge is this, correct? Because for I type instructions, the RT, this register, is specified by the bits 20 to 16. This is already the way the instruction encoding scheme is designed. Okay, so for I-type instructions, okay, the destination register or the final register where the result is supposed to be stored back to is specified in RT, and RT's bit location is 20 to 16. Okay, but the current wiring that we have done maps these bits 20 to 16 to read register 2. Okay, but that is not what we want, because since we are intending to write back to register 21, I need this to actually come over here. Okay, because the bits 20 to 16 is actually representing RT, which is the register that I'm going to write back to. Okay, so that is the current sort of challenge that we are facing. All right, and the way to overcome that challenge, that means how do I make it come over here for I type. For R type, I want it to carry on over here. But for this R type, okay, but for I type, I want it to come here. Okay, and the way I can do that is by using this additional hardware called a multiplexer. So this multiplexer will then decide whether the RT bits gets channeled to the right register or it is the RD bit location. So this 15 to 11 is actually the RD bits. Okay, the RD bits if it was the R type. Okay, but for I type there is no RD, correct? It's only RS and RT. Okay, so that is the reason why we now need a multiplexer here to decide whether to take the RT bits location or RD bits location to specify as the right register. Okay, so that is the first change now that we are doing to support the I type instruction. Okay, so that is the uh, the first step, okay, that we have done. Now the next thing is this, the choice in data 2. All right, so maybe let's go back here first. Let me go back to the R type. Okay, so that you can see the reasons. Huh? So for this instruction, we know we're going to do an add operation, correct? And to do this add operation, we are going to use two data, and the two sets of data are actually coming from both the registers, one from RS and one from RT, and both of it is available here. Okay, that means basically what is the next step? I take both of this data, pass it to my adder. Correct. Okay, so we can see it's quite straightforward. Huh? I specify the two registers where I want to read data from. Both the data come out from my register file, and once both the data come out, I can go in and perform the addition. All right. So that is the R format instruction. Okay, so I can straight away take both this data and pass it into my ALU stage. Okay, so that's the next stage we're going to talk about. Okay, but basically we know the operation is the add operation, and I can do that with these two data. But now when it comes to I type instruction, okay, for I type instructions, what is happening? We are now doing a add with immediate, add with immediate. So one of the data is the data in register 22, which is this. So this one we got it ready. Okay, but the second data is not from a register. It is specified in the instruction. Okay, the second data is not from a register. Okay, it is from the instruction. So it is this immediate value over here. Okay, so when I go on to the next stage, I must be able to send the correct data to the ALU stage. All right, so that it can perform this addition operation with the correct data. So one data is already available here, the content of register 22. How about this negative 50, which is in the instruction, which is not from the register file? Okay, so what I need to do, again, I need to use a multiplexer. Okay, again, I need to use a multiplexer to be able to select between two different data. One is, of course, this data. Okay, because we just saw that for R type instruction, I want the data from both read data 1 and read data 2. But now for I type instruction, I now have to include the option that the second data is not going to be read data 2, but it's going to come from my immediate field in the instruction. Okay, it's going to come from the immediate field in the instruction. Okay, so that is where this multiplexer comes in. So this multiplexer's job is to decide between the two type of data. One is the read data 2. Okay, the other is the instructions, the 16-bit data already specified in the instruction. Okay, so now there's one more block here, which is called the sign extend block. Okay, so what is sign extension? I think I briefly talked about it in one of the earlier lessons. Okay, so sign extension is basically to take the most significant bit and extend it. Okay, why you want to extend it? Because your entire processor is designed to handle fixed data weight, correct? In our case, it's 32-bit. Okay, so all your processing is 32-bit. But in our instruction, okay, if you look at ITAC instruction, this immediate field is only 16-bit. All right, but when I go to the next stage, which is the ALU stage, all the operations are done as 32-bit operations. Okay, so in order to support that, I need to extend my 16-bit to 32-bit. So that's why you see before that it is 16. After I do sign extension, it becomes 32. Okay, how to do the sign extension? You just need to look at the most significant bit. That means if when I look at my data, if let's say my most significant bit is 1, starting from 1, okay, doesn't matter. So if I look at the 16 bit and I say that the most significant bit is a 1, that this 1 gets copied over 16 times. Okay, and then I get a full 32 bit. Okay, if the most significant bit is 0, if the most significant bit is 0, then this 0 gets copied over and everything else becomes 0. Okay, it is basically the idea of the two's complement. If you remember two's complement notation, you can differentiate whether it's plus or positive or negative looking at the most significant bit, because that specifies the sign. Correct? So when the most significant bit is 0, then we say it's a positive number. If it's a 1, we say it's a negative number. So by extending the most significant bit out, it does not change the value in any way. Okay, it is the same value. All right, so that is the way the two's complement helps us. All right, you can just extend the most significant bit and yet the value does not change. All right, so that is what we are doing for the sign extension. We are taking the 16-bit value and we are extending it. Okay, so if you look back at the calculator, okay, if you look back at the calculator, you can see that the same negative 50, okay, is actually specified whether it's 16-bit, 32-bit, or 64-bit. All the ones in front makes no difference because it's just a sign extension. Okay, so as long as the most significant bit is 1, all right, if I extend, it makes no difference to the value. All right, so that is how the sign extension works. Okay, and that is what we need to do in the processor to make the 16-bit become 32-bit. And this multiplexer over here will then help us to decide between either taking the 32-bit data from the register file or taking the 32-bit data from the immediate field of the instruction. Okay, so you can see that we started off with a very simple design, but now we are slowly making changes to accommodate the different type of instructions that your processor is going to support. Okay, so that is where all the multiplexers all come in, because those help us to decide at any point of time which data goes to the next stage. Okay, and now we also introduce another control signal called the ALU source. So we had register write, okay, we had register destination, and now ALU source. So ALU source, as the name suggests, is deciding the source of the data for the ALU stage. One source is fixed, which is this. Okay, one source is fixed, okay, which is the read data one. The second source is the one that we need to make a decision. Is it read data 2, or is it the data coming out or extracted from the immediate field of the instruction? Okay, so that is the decision that we will make through this multiplexer and control signal. Okay, yeah, how about load word instruction? Okay, do I need to do any modification to the processor if I were to do or perform this load word instruction? Okay, so in order to answer that, we first need to relate this instruction to the instruction encoding. Okay, so the first thing is load word. Okay, so load word, you can look back at your instruction set here. Okay, so load word is specified as 23 hex. Okay, it's 23 hex. So okay, so this is 23 hex here. So this is hex 23. Okay, and this negative 50 is over here, negative 50, the immediate field. All right, and this is your RS and this is your RT. Okay, so this is your 22 over here, and this is 3. This is 21. All right. So let's just understand the instruction again. So what is this instruction going to do? It is going to take some load means take some data from memory and move it to a register. All right. Take data from memory, move it to a register. So where in memory? Where in memory is the part that is specified by this second half of the instruction. So I take the content in register 22, add with the immediate, which is negative 50, and this whole thing is pointing to the memory location. Correct? Okay, so that is what this instruction is supposed to do for us. When I look at this instruction, what it's supposed to do, and I look back at here, in this instruction here, do you see any difference in the first part of it? The first part of it is exactly the same. Correct? Why is it exactly the same? Because we are going to take the content of register 22 and add with negative 50 over here. All right, but in this case, that result is actually the answer already. Correct? But in this instruction, we are still doing the same thing. We are taking the content of register 22, add with negative 50, but now we're going to take this result to point to a memory. But this part over here is still the same as before. Correct? So that is why over here 22 means the content of register 22 will come out. Correct? And this 16-bit immediate value will get extended to 32-bit. Okay? And that will then be channeled to go out over here. Okay, exactly the same as over here. Here also we will do the same thing. We'll channel this data out. We will not take the read data too. We will take the immediate value, which is sign extended. Okay, to go to the ALU stage. So we have not done the addition yet, but you can see that the first part, which is where the data comes from, is actually the same in this instruction, which is the add I instruction, and this lower instruction. Though they are totally two different instructions, okay, with different outcomes, the first part is the same. That means in both these instructions, I'm going to take the data from register 22, add with the immediate value negative 50. All right. It's just what I do with the result that is different. In one case, I take that as the final result. In this case, I take that to point to a memory. All right, so that is the difference. So since the first part is the same, you actually do not need to make any changes to your processor architecture to support this low word instruction, correct? So no modification is needed. Okay, how about BEQ? Okay, so for BEQ, what do you see? You have two data, register 9 and register 0. Okay, so this here is your 9 and this here is 0. Okay, and this is your immediate value 3. Okay, and I'm supposed to do a branch if the contents of register 9 and the contents of register 0 are the same. All right, and what is going to happen here? Since I'm specifying 9 over here, RS, so I'm specifying register 9, and here is RT register 0. What will happen? The content of register 9 will come out here. Okay, and the content of register 0 will come out here. Okay, and of course, since I already have a multiplexer here, okay, I channel this to go out. Okay, so you can see that the design that we have currently supports the BEQ instruction as well. Correct, because I'm able to read the data from register 9, read the data from register 0, and send it out to the next stage. Okay, right now we have not done any of the arithmetic or logical operations yet. We are still looking at the stage where I make sure the correct data is sent through to the next stage. And you can see that with this current design and with the multiplexers we already have, I am able to select the correct data to the next stage. Okay, so of course, what is not yet shown is I need to also calculate the branch address, correct? So that one we will look at it later. But so far, the current design is fine. Okay, I can support my R type, I can support I type, I can support the branch instruction. So you can see that currently what we have, this design is good enough to support the instructions that we have looked at so far. Okay, so that is the decode stage. Okay, so before I go on to the ALU stage, does anybody have any questions you all want to ask or clarify about the decode stage so far? Okay, because I want to make sure you all understand this stage correct first, and then we can go on to the next stage.
Yeah, I have a question regarding the I format at I.
Yes.
Yeah, correct. Yeah, this slide. So we are reading the RT into register 2, right?
Yes.
But actually we don't need that data because we want to write the data into register 2.
Yes.
We don't need to read it.
Mm.
So isn't it a waste of time to read the register 2?
There is no additional wastage of time. Okay, so maybe let me explain the question so everybody understands. So the question is basically that, okay, so in this case what is happening is I specify 22 over here, correct, and I specify 21 over here, okay, and 21 also comes here. Okay, 21 also comes here. All right, and since in this case I am going to use 21 as my write register, so I will configure register destination such that this gets selected. So 21 comes here as the register I want to write to. Okay, so that part is what we know from the multiplexer configuration here. But okay, what the question is being asked is, since 21 is specified as read register 2, the content, okay, of register 21 will also come out here. All right, so that is the way the hardware is really designed. Okay, you will see that not only in these cases, later on there will be many processing that is done, a lot of processing that is done that is in many cases redundant. Okay, we will not actually use it. All right, but it does not add any additional delay because both this data, the way the hardware is designed, is both read data 1 and read data 2 will come out together at the same time. Okay, so it's not one after another. So either way, you will wait for the same amount of time for data to be ready after the register file operation. Okay, so it is not additional time. So in that sense, we will not incur any penalty because of this. And later on, you will also see that we will have other blocks, okay, that are in a sense redundant, but we will still do it. Okay, so for example, branch instructions, you will see that we will calculate the branch instruction anyway, even if it's not a branch instruction. So I mean, we will calculate the branch address anyway, even if it's not a branch instruction, because we always want to stand by the data to be ready for us to use, okay, at a later stage later on. Okay, so let me look at the question, the load word instruction. Okay, so for the load word instruction, okay, this instruction is basically specifying the operation where we want to take data from a memory location, okay, and move it to memory, move it to an internal register. And the address that we are going to point to is specified by this. Okay, it's specified by this, which is the content of register 22 Okay, add with the offset. Okay, so the format of instruction we have gone through before already in earlier classes. So 22 means the content in register 22, add with the offset -50. Okay, and that gives me the final address of where I want to point to in memory. Okay, so of course that is later part of the processor, but in the first part, what are we doing? We are taking the content of register 22 and we are adding it with an immediate value which is -50. Okay, so this first part here is actually the same as this instruction. Okay, taking the content of register 22 and adding it with an immediate value of -50. All right, so it is the same. The first part of what you're going to do is the same, and the current processor design that we saw supports this without any further changes, because 22 is specified in your RS, so the content of register 22 will come out here, and -50 is specified as your immediate value, which will then get sign extended, and then you will channel it out over here. Okay, so the processor design supports this instruction as it is already without any further changes needed. Okay, so that was what the objective of this slide was. Okay, to show you that the current processor design for the decode stage is now able to support your R type, your I type, as well as your BEQ. Okay, so all three types of instructions can now be supported with the current design that we have. The decoder doesn't output the right. Okay, so the right register information is extracted from the instruction itself. Okay, so if I look back here, okay, so let me go back here. So in this instruction here, we can see that the right register here is register 21. Okay, so 21 comes here and it also comes here. Okay, it comes to both of these places. So since I specify read register 2 as register 21, the content of register 21 also comes here. Okay, that is again a default behavior. Okay, we can't change that. All right, but of course, since we have a multiplexer here, we can decide which data we want. Okay, but in this case, we know the data coming out of the instruction field is what we want, so that part is settled. Now for the right register portion, we have this multiplexer. All right, so this multiplexer, we will now select it so that the register 21 is now specified here as the right register. Okay, so the read registers and write registers are already known the moment the instruction is decoded. Okay, the information that we currently still do not know is the right data, because this is only available once your instruction goes to a later stage, okay, which we will come to soon. Okay, but the right register information is already known.
Sorry, I got another question. My question is pertaining to the what happens after we send the data to the ALU. So after the data is processed by the ALU, must we go back to the register file again?
Yes,
to
yes,
feed in the data?
Correct. Yeah, we will be coming to that after a while.
I see.
Yeah.
Okay.
So we are still at the decode stage. Okay, so fetch, decode, execute, and then write back. Okay,
And
so currently we are still at the decode stage. Okay, we will be coming to that in a while.
My other question is, how do we program the multiplex? How do we
okay, so
how does the multiplex know?
correct. So the multiplexers are all controlled through these various control signals. Okay, and these control signals are generated by a control block. So that is actually the next chapter. Okay, so there are many control signals we will see later on as well. And these control signals are very important because they are the ones that decide how data will channel through from one stage to the next stage. Okay, which data is selected and where does it go to next. Okay, so these control signals are generated based on the information that you get from the opcode as well as the function field. All right, and this we will discuss. Okay, this process of decision making is actually for the next chapter. Okay, but for now, what what you need to know is that these will be generated based on the instruction we are decoding, the instruction we are trying to execute. Okay, and the control block will be able to generate the correct signals for us. Okay, so that the data that we want will pass through from one stage to the next stage correctly. Okay, so how does the next stage know register 21? Okay, so the next stage will not know where the data came from. It will only know that the data is now ready and will process the data according to the operation that is supposed to carry out. Okay, so right now, for example, in this case, what is, okay, if I were to draw okay, I want to draw a line here, okay, to say that this is the end of the decode stage. So what comes out of the decode stage? What comes out of data decode stage is just two sets of data, correct? Okay, when we look at the decode stage, we know that one set of data is the content from register 22, and in this case, the other data is the instruction -50, which has already been extended to 32-bit. All right, so of course we know the information because we looked at the decode stage. But if I mask out the decode stage and I look at what goes to the next stage, you only see two 32-bit data. Correct? Two 32-bit data is coming out of the decode stage and going to the ALU stage. As far as the ALU stage is concerned, which we will look at later, it is supposed to take this data and perform the correct operation for us. It does not care where the data came from. Okay, whether data come from register, come from instruction, that is not the issue for the ALU stage. The ALU stage is supposed to take the data and perform the correct operation for us. Okay, so that is what we will look at next. Okay, so I think it's a good time to go for a break now. All right, and so now it's about 8 o'clock. Okay, we'll take about 20 minutes break, 8:20. Okay, and then we will come back and then we will look at this in more detail. Okay, so your questions you can just put in the chat first. Okay, later when we come back from the break, I will answer all your questions. All right, and then after that we will go on to the next stage. Okay, so you can go for a break. Questions, just put it in the chat first. After when we come back, we will go through all your questions and make sure everybody is clear before we go on to the next stage. Okay, so I'll see you all back here at 8:20. Okay, so hope everybody is back after the break. Okay, so there is one question. Where is the register file stored? Okay, and okay, so the register file, okay, the register file is basically is a single register file for the entire processor. Okay, so every time you fetch, okay, so you have to remember that we are executing one instruction at a time. Okay, so when I fetch one instruction and I load it into the processor, all these sequences will happen until the instruction is complete. Then the next instruction comes in. Okay, so the register file is used as a place, okay, for the various registers to hold information for us for each instruction, and at the end of the instruction, in some cases, a register may be updated, okay, with some new value. Okay, so if I look at this instruction, for example, I will take the data from the memory and eventually update the register 21. Okay, so when I finish this instruction, okay, then register 21 will have a new value, which will be the data I fetch from memory. Okay, if I look back at the earlier instruction, this instruction here, for example, register 21 will also have a new value, but that register 21's new value would be based on the addition operation between the content of register 22 and negative 50 immediate value, and that result will be stored back in register 21. Okay, so you have a single register file. All of this hardware that we are seeing is just a single copy that will be inside the processor block. Okay, and every time a new instruction is fetched in, I will use this hardware to execute the instruction, get the desired output, and then when it's finished, then I go on to the next instruction. Okay, so this is where we stopped. Okay, the decode stage of your system. Okay, and in this current design, we can see that it supports our R type, our I type, and our branch instructions well. Okay, no issues. Okay, and another thing that we also talked about just now is the fact that there will be operations carried out by different parts of the hardware that you will see that is actually not being used in that particular instruction, but it is still done anyway. Okay, so that is where the hardwired hardware blocks come in. So the idea is we want to prepare in advance as much of the information as we can, and along the way we will decide which of this or which parts of this data or information we want to use for the next stage and so on. Okay, so that is the whole idea. Okay, so now we have completed the ALU stage, and with the ALU stage, the whole idea is we want to perform the correct execution. Okay, so when you say correct execution, it could be performing the addition or subtraction or shifting or anything or logical operations, okay, or performing the address calculation to perform the correct memory access later on, or it could also be making the decision for some branching operation. Okay, so the previous stage is the decode, and the next stage is the memory stage. Okay, so let's look at the ALU. So the ALU, like I said, what the ALU sees is two 32 bits of data, two sets of data, each set is 32 bit, and it's going to perform a particular ALU operation and give us the result. Okay, where these two data come from, that is the responsibility of the decode stage. So that is what we just saw. So the decode stage looks at the opcode, okay, the function field and everything else, and with the multiplexers and control signals, makes sure that the correct two sets of data is passed over to the ALU stage. In the ALU stage, okay, we perform the necessary logical or arithmetic operation to give us the correct result. Okay, so you have two 32-bit numbers, okay, and at the same time you have ALU control. Okay, again, this is part of the control unit. Okay, part of the control unit, which we will cover in the next lecture. And the control unit will provide us with the necessary control signals to ensure that the multiplexers, the ALU, and so on perform according to the instruction we are executing. Okay, so that is the idea here. Okay, just give me a minute here. Okay, sorry about that. Okay, so as I was mentioning, the control unit, we will look at it in more detail in the next lecture. But for now, you just take it that all these control signals will be generated correctly depending on whichever instruction we are executing. Now, for the ALU output, you see two output. One is, of course, the A and B and the correct operation. The operation is, of course, decided by the ALU control. And there's also one more additional output that is generated, which is what we call the is0 bit. Okay, and this is0 bit is to indicate whether, okay, the output, okay, of the operation is actually equals to 0. All right, so this additional bit, Okay, this single bit that is generated as a result is used to indicate whether the output is 0. I mean, the output of the operation that we have carried out, is it equals to 0? Okay, and why this is helpful for us is it helps us in making the branch decisions later on. Okay, so we will look at that. So these are the ALU control bits. You do not need to worry about how we generate these control bits. Okay, so that is not covered. But as you can see, each of these control bits are unique. All right, and with these control bits coming in, we are able to select the correct operation, okay, for the ALU to carry out. Okay, so now let's look at this. For until here is what we have already seen, okay, up to the decode stage. Okay, so up to this was the decode stage. All right, for the ALU stage, no issues. All right, in terms of okay, if you look back at decode stage, we can say that the RD is the one that is going to come here, okay, because this is your destination register. This is your 9, this is your 10, this is your 8. Okay, so 8 is your write register, and in this second multiplexer, we are going to select the RD2. So this is your RD1, and this is your RD2, and this is the content from register 9, and this is the content from register 10. Okay, both of this data will be channeled to the next stage, which is the ALU stage. All right, and with this two data going in and the ALU control specifying that I want to do a add operation, okay, the result will be available here. So what I will get here is the content of register 9 add with the content of register 10. Okay, that is the result. Okay, now, so of course this result later on we will use to write back. Okay, in a later stage we will discuss that in a while. Now for branch instructions, okay, we need to do two things. One is we need to use the ALU to compare whether the branch is supposed to be taken or not, and that is where the E0 bit comes in. Okay, so equal or not equal check. Okay, we can decide by using the E0 signal, and then we also need to calculate the branch target address. Okay, so this is also the short form we call it BTA, the branch target address. In this branch target address is basically your PC plus 4 plus the offset over here. Okay, so we need to take this offset. Okay, so if you forgotten, you can look back at the earlier slide. This tells us the number of lines. Correct. So this tells us that from PC plus 4 is 3 lines away. Okay, and then I need to branch to that particular line. Okay, so the target address that I need to jump to is your PC plus 4 plus 3 lines away. Okay, so I need to also calculate this target address. Okay, so that is where this new part comes in. All right, so in this new part, what do you see? Okay, you see that the instruction, okay, bits which are the lower 16 bits, the immediate field, okay, which is now over here, this one, bit 15 to 0. Okay, that 15 to 0 will now be extended. After it's being extended to 32 bit, it will now left shift by 2 bits. Okay, why left shift by 2 bit? Because left shift by 2 is the same as multiplied by 4. Okay, and why multiply by 4? Because it is 4 bytes, okay, per instruction. Okay, 4 bytes per instruction. So when I say it's 3 lines of code, that means it is equivalent to 12 bytes away. Okay, because one instruction or one instruction line is 4 bytes. Okay, so the PC has to be adjusted by a certain number of bytes. Okay, how do I calculate the number of bytes? Is based on the number of lines of code. So 3 lines of code means it is equivalent to multiplied by 4, which is 12 bytes away. All right, so that is why I do a left shift by 2. All right, and then over here what I have is PC plus 4. Okay, because this is PC plus 4 already done here. Okay, and this has now passed, is going to pass through another multiplexer, and this multiplexer has 2 inputs now. Okay, one is PC plus 4, and this one is PC plus 4 plus your immediate times 4. Okay, so there are 2 inputs now to the multiplexer. All right, and you now have another control signal called PC source. So this PC source will be activated to decide whether it is supposed to go to the next line or is supposed to take the branch and go to a new line. Okay, so that is this additional piece of hardware that is going to help us to always calculate this address that we are going to potentially jump to if the branch is taken. Okay, so that is your extension of your branch. Okay, so extension of the current design to incorporate the hardware for the branch. All right, so now if you look at this, it relates back to what I said earlier of redundancy. Okay, where we are doing work which may not be used at all. Okay, now if I this hardware that we just added here makes sense when we're talking about a branch instruction. All right, but if I were to give you an instruction like this, the add, okay, register 8, 9, and 10, the earlier instruction, the RTI instruction, which has no branch, which has no immediate value. All right, but whatever is the case, you will still take the lower 16 bits. Okay, you will still take the lower 16 bits. You will still extend it to 32 bits. All right, now the lower 16 bits make no sense for RTA instruction. Okay, the lower 16 bits makes no sense because there is no immediate value in the lower 16 bits. Okay, but your processor is already hardwired in a way such that the lower 16 bits will be taken. You will do a sign extension. You will present it as one of the input to the multiplexer here. You will multiply by 4, add with PC plus 4, and also present to this multiplexer here, even though it makes no sense for a R-type add instruction. Okay, because these are all hardwired to behave in this particular way. All right, and the reason why we do this is we want the hardware to preemptively prepare as much information as possible so that when a decision is made, we can quickly carry it out. All right, okay, we do not want to wait until we finally know whether the branch is to be taken or not and then go and do all this calculation. All right, so there is no additional delay because later on when we look at the timing analysis, okay, in the tutorial, you will see that operations like the register file and the ALU and so on are going to take much longer compared to operations like the add, the left shift, sign extension, and so on. Okay, so whatever the case, all these smaller blocks of hardware are going to be much faster than these bigger blocks of hardware. All right, so we are not going to add any delay. We are just making use of the current available time to prepare the data as much as we can. All right, and then later on, using the multiplexers and the control signals, we will decide whether to use this data or not. Okay, so that is the idea behind the way it is designed, the whole processor. Okay, so now let's go on to the next stage. So next stage is the memory stage. Okay, so in this memory stage is where we are going to access a memory. Okay, so memory access is either through load or through store instructions, and only these two instructions have memory access involved. The other instructions do not. Okay, and what we then need to do is take when we execute this instruction, either we are going to update the contents of the memory location, or we're going to take the contents of the memory location and update a register. Okay, so in terms of memory, we can simplify it to a block like this, where you have two sets of information. One is the 32-bit address, okay, and next is the 32-bit data. Okay, so one is address, one is data, and then you have two control signals, mem write and mem read. Okay, so this mem write and mem read are control signals which will be generated according to the kind of operation you are going to carry out. All right, and then there is also the option to read data. So you can write data or you can also read data. So depending on whether you're doing a load word or a store word. When I'm reading data, the objective, the final endpoint is when I read the data, I want to update it to one of my registers. Correct? So if I would execute the instruction load word S0 with for S1. Okay, the idea is at the end of this instruction, whatever data I take from this memory, I update into a register. Okay, so that is where the read data comes in. So I read from the memory and update a register. Okay, so these are all the things I just talked about. Okay, so now let's look at how this behaves, okay, for this instruction here. All right, so for this load word instruction, okay, so we know that 22 comes here. Okay, this is 21 and this is -50. All right, so here I'm specifying 22, register 22, so that content in register 22 comes out. Okay, the content inside register 22 is now available in RD1. Okay, 21 is specified here and it's also coming here. All right, and since I know this is a load word instruction, okay, this is my RS, this is my RT, and RT is the register I need to write back to. Correct, so I will configure my register destination so that this gets selected to come here. So 21 will come here to specify that that is the register I want to write back to later on. All right, so this RD2 also has content of register 21. Okay, also has content register 21, but we are not going to use this. Correct, because the ALU operation we are going to carry out is what? The ALU operation is the content of register 22 add with -50. Okay, so the two source operands for my ALU is this. One is content of register 22, that is this. The second one is my immediate value of -50, so that is this. So that will go through the sign extension, come to the multiplexer, and this multiplexer will be configured so that I use this option. So this will be -50, but already sign extended. Okay, so now you can see that this is basically what we discussed earlier, until the decode stage. Then what else is going to happen? So since I am doing a load word operation, I know that the objective of the ALU would be to perform a addition. So my ALU control bits over here will tell the ALU that I need to do a addition operation. So when I do an addition operation between these two sets of data, this result is referring to what? The memory I want to access. Okay, since this is the memory you want to access, you take the data and present it as the address to the memory. So the address that you present, okay, or when you present this data to the address bus of the memory, you are telling the memory that this is the address location you are interested in, either to write or to read. Okay, so that is why the result of the ALU is connected to the address bus of the memory. Okay, so you remember that in this case, we are doing the addition operation, and the result of this addition operation is to point to a memory location. Okay, so that is what is being done here. Okay, so this whole thing is what comes out here. Where I point to a memory address. This is a load word instruction. So since the load word instruction, your mem read will be activated. Okay, so mem read, mem write, these are also control signals. Okay, which will decide the behavior of all these subsystems. So in this case, since it's a load word, I'm going to do a mem read. So when I present to the data memory the address that I want to read from, and I activate the mem read line, what will come out? The data that I want will come out on the read data lines. Okay, the data that I want will come out on the read data lines. Okay, so you can see how everything is sort of linked together and leading up to help us complete the whole instruction. Okay, so first we talked about the instruction encoding, the register file, the decoding, the ALU, and now it's at the memory already. Okay, so I've done everything. I've generated the address that I'm interested in. I have sent that address to data memory. I've activated the memory line, and then the correct data will now appear on the read data lines of the memory. All right, so that will, of course, you still need to use that to write back, but in a while we'll come to that. Let's look at Stalwart. Okay, so Stalwart is we need to do some other modification. So let's first look at Stalwart instruction. The difference between this and this is what? Is exactly the same, except that it is from load word becomes Stalwart. All right. So the RS and RT have not changed. This is still your RS and this is your RT. Okay, so RS and RT have not changed, and what you're doing here again has not changed. Okay, again has not changed, because what you're doing here is you're taking the content of register 22, add with negative 50, and this whole thing is point to a memory location. Okay, so all the stages have not all the earlier operations that we saw for load word will still carry on over here. Okay, 22 will come here. Okay, 21 will come here. 22 content will come here. Negative 50 will be here. I will extend it and I will put it over here. All right, and 21 will also come here. All right, but now, okay, in this instruction, this Stalwart instruction, do I need to do a register write? Okay, do I need to do a register write? Okay, okay, so in this Stalwart instruction, what are you doing? You are taking the content of register 21 and storing it into a memory location. Okay, so there is actually no register write involved. What is being done is a memory write. Okay, in the load word instruction, you are doing a memory write. You're doing a memory read and register write. Okay, this whole thing here is the memory read. Okay, and once I read, I want to take this data and do a write to register. Okay, we will look at that in a while. But the load word instruction is the address points to a memory. From the memory, I take the data and update a register. So there is a register write involved. But a store word instruction, you are taking the content that is already in a register and you're going to write it to a memory location. We're going to write it to a memory location. So the register 22 content plus -50 is pointing to the address. But in this case, you are activating the memory write, not memory read, because it's a store word. Store word means take data from register and write to memory. Okay, take data from register and write to memory. So the mem write signal will be activated. Okay, so when the mem write signal is activated, the address we have already calculated, okay, which is 22, content of register 22 plus -50. That is the address I'm pointing to. So the data is where? The data is actually here, register 21. So this data is, since it's specified here in read register 2, okay, it will be available. Okay, it will be available over here. Okay, it will be available here. Okay, so the content of register 21 will be here. So that is why now we have added this new line over here that will now connect to the right data pins of your data memory. So previously we didn't have that line. Okay, but here we have that line. Okay, and you can see that there is no multiplexer there. Okay, that RD2 is directly connected to write data. Okay, so the question here in the chat is, how does the processor know to put RD2 into write data? Okay, so this is hardwired. It is always connected. That means RD2 is always connected to write data. All right. So of course, then the next question is, does it mean I'm going to write all the time? No, correct. Why? Because I will only write when my mem write is activated. And my mem write will be activated if it is a store word instruction. Okay, so that is again linking up to the control block. So the control block, okay, will help us to decide when to use the data in different parts of the processor and move it along, okay, to the next stage and so on. Okay, so RD2 is always connected to write data. Okay, but you are not going to write data to the memory, or you're not going to change any memory content unless mem write signal is activated. And mem write signal will only be activated whenever you are going to perform a store word instruction. Similarly, coming back to here, load word. The ALU result is always connected to the address bus of your data memory. Okay, it's always connected to the address bus of your data memory. All right, regardless of whether it is a load word instruction or add instruction. Okay, so even if I say it's an add instruction, Okay, okay, it is still connected. All right, of course, uh, how do we differentiate, or what do we do? Okay, so let's look at this from the next slide over here. So you can see that in this slide, the ALU result, okay, like what I mentioned just now, is always connected to the address. All right, but it doesn't mean that I'm all going to be updating the memory all the time, because again, it links back with the control signals, whether I'm doing a mem write or mem read. If mem write or mem read is not activated, then even though the address bus has some information, I'm not going to change anything or access any part of the memory. All right, but in a situation like this where your instruction is an R type instruction, all right, the ALU result is actually the answer already, all right, because 9 add with 10 is already the answer which I want to write back to it. All right, so in order for me to take this data and channel it back, so if you look back at this instruction and this instruction, you will see that in both these instructions, okay, I'm taking some information and I need to write back to a register. All right, but for a load instruction, the data is coming from the memory. In a R type instruction like this, the result is the ALU result itself, nothing to do with the memory. Okay, so that is where another multiplexer comes in, called the Mem To Register Multiplexer. And for the Mem To Register Multiplexer, it is to decide which data gets channeled back. Is it the data coming out of the memory? Okay, so this would have been a load word instruction, or the data coming in from the ALU. So this is the direct ALU result. Okay, so one of it will be selected to pass through to the next stage. Okay, so as a question, read data output is only useful for mem read. Okay, so yeah, the read data and write data are only useful when you have a load word or store word instruction. Okay, so if I have a load word instruction, then I look at read data. If it's a store word instruction, then there is the write data. Okay, if only these two instructions are going to access your memory. Okay, all other instructions will not access your data memory. So you do not need to worry about the memory interface. All right, so that is why we have another multiplexer here to differentiate and decide which data I actually want to be channeled back. All right, so now we are at the last stage already. Okay, the last stage, all right, where you have the data and you want to make sure that this data is now written back to the register. So that is where the write register and write data comes in. Okay, so we have seen just now that the write register information is already available the moment you fetch the instruction. Okay, the moment you fetch and decode the instruction, the write register information is already available. What you now have is actually the write data, because you have either completed the ALU operation, which is in this case over here, so the result is available, or you have completed a load word instruction and you have already accessed the data from the memory. Okay, so right now the data that you want is also available. All right, so looking at this, what all you need to do is there's only two ways data is going to come back to be written, either from the memory, if it was a load word instruction, or directly from the ALU. Okay, and that is where this multiplexer will decide and channel it back. So if you look at this red line, it goes back to the write data. All right, the write register was already known to us the moment we decoded the instruction. Okay, and using this multiplexer, you are able to select the correct right register to specify to the register file. Okay, so you can see that right now the entire data part is complete. Okay, so obviously we are not covering all the instructions, all right, because then your processor will just grow and grow and grow. Okay, so what we are going to cover is only up to this portion in terms of the processor architecture design. All right, so if you look at this whole picture right now, okay, you can see that you can sort of trace through the entire sequence of the multiplexer, the register file, the ALU, and so on for add operation or uh, I-type instruction or a branch instruction and so on. Okay, so each of these instructions will have data passing through different parts of the processor, okay, at different stages. And it depends on, of course, the multiplexers, which are linked back to the control block. Okay, so the control block will decide, okay, how we are going to link up everything together. Okay, so I will stop here first and take questions that you have. Anything you want to clarify from what we have discussed so far? Okay, anything you're not sure, okay, about the different instructions, the wiring, the multiplexers, and so on? All clear? Any questions? Okay, yeah, so being a bit confused and not very sure is fine. All right, uh, I guess it is normal. Okay, so no need to be too concerned. Okay, it takes time to go through the whole sequence, okay, and then see everything for yourself. All right, so after I upload the recording, then probably you can go through step by step and then relook at it. Okay, so the multiplexer is again hardware we introduced to you here, uh, again because is needed for you to understand how we are able to select between different inputs and just select one of them to be channeled to the next stage. All right, and the reason why we have all this is because we want to keep the processor design uh, as simple as possible by reusing as much of the blocks as we can. Okay, if you want to design uh, one set of register file, ALU, everything for R type, then another copy paste for I type, and then another type. Okay, your whole hardware will become very, very big. All right, so the idea is we already have a register file, we have ALU, we have memory and everything. And what we want to do is we want to be able to uh, reuse the same hardware, the main blocks, and get uh, fulfill all the different type of instructions that we want. Okay, so we need to be able to make decisions on how data is going to move from one stage to another stage and so on. Okay, and that is where all these multiplexers and control signals come in. Okay, so there's a question of the load word and store word. Okay, so let me just put it out separately. Give me a minute. Okay, so there's one more question. Is a program counter a special register to time the instructions to the processor. Okay, so you can think of it, yeah, something like that. All right. So every sort of computing system has to have a clock, correct? Has to have a clocking mechanism, and that clocking mechanism tells us how fast it's able to execute instructions. Okay, so in our case, to put it simply, you can say that every clock, okay, of your processor, a new instruction will be fetched and passed in, okay, uh, to for the processor to execute. And when everything is complete, then the next instruction will be fetched. All right. Of course, you can say that it sounds very slow, correct? Because then I need to wait for the instruction to be fully complete. Then only the next instruction can load and start to execute. And different instructions will take different amounts of time, correct? Because instruction that don't use memory will execute faster compared to instruction that use memory and so on. Okay, so of course that is of course, to put it very simplistically, because this is the idea of a single cycle processor. So what we are covering is what we call a single cycle processor. That means in one clock cycle you execute one instruction. That means your processor speed is limited by the slowest instruction. Okay, of course, to counter this, there are a lot of improvements in the architecture, and one of it is the idea called pipelining. Okay, in pipelining, what we do is we break up the entire processor into different stages, and then we sort of save that stage and allow you to go on to and fetch the next instruction while the previous instruction is still being executed. Okay, the idea is, like, for example, you go from place A to place B. If you carry the same object from A to B, one person at a time, then it will take very long, correct? If the entire place you have 5 of you standing together, you just pass around, then it's very fast, correct? So that idea is what we call a pipelining processor, but we are not covering that. Okay, if you're interested, I can share those notes with you. Those are things that the full-time students do. Okay, but in our case, we are not pipelining. All right, I mean, we're not covering the pipelining part. All right, but I can share those material with you if you're interested. Okay, pipelining happens in different stages. That means you look at the 5 stages: fetch, decode, execute, memory, write back. That means for all these 5 stages, there is a pipeline stage. That means there's a buffer stage to hold information while you move from one stage to the next stage. All right, so that is the idea of improving your system. Okay, so let me just go through this load word and store word, okay, to be clear, so everybody understands. So for this instruction over here, we see the load word. All right, so this is again your RS, this is your immediate, and this is your RT. Okay, so this is your 22, this is 21, and this is -50. All right, so for load word, what will happen is you get 22 over here, 21, 21. Okay, and what comes out here is always the data in register specified by the RR bits here. Okay, so what are we trying to do over here? We are trying to take the data in register 22 at bit -50, correct? And this is points to memory, points to a memory location. All right, so what I need to do is I need to take these 2 source of data and perform the add operation. So this first one is already available, okay, over here. Now this second one is -50 is available through the 16 bits, and these 16 bits will get signed, extended, and come here. So over here, I need to make sure the ALU source is configured to make this come through here. Okay, the immediate value. This add operation the overall responsibility is through the control block. So the ALU control will tell the ALU unit that I need to do an add operation. And after I do the add operation, what I get over here is this, the address of where I want to point to. Okay, and since this is a load word instruction, okay, the load word instruction will again activate the control signal memory. All right, and when memory is activated and I have an address given to the data memory, the appropriate data will now be available over here. Okay, and that is where the data from here will go back. Okay, so of course there's one more multiplexer here, okay, which is not shown. Okay, then this data will then go back to the right data. Okay, the register, the right register is already specified through this instruction and the correct multiplexer selection over here. Okay, so that is your load word. So in load word, you are performing an addition operation for the ALU part, but that addition operation is not the result we're interested in here. That is to point to the memory, and what we're interested in is the data inside the memory. All right, and that will channel back to the register file to be updated to whichever register we specify over here. Okay, so that is your load word. The other one is your store word. Your store word again is very similar. So this is your RS, and this is your RT. So this is 22, 21, and negative 50. Okay, so you have 22, 21, 21, and negative 50 over here. So the same thing happens, correct? The same thing happens. Over here, I have 22, the content of register 22. All right. And here I have the content of register 21. Okay. Previously, also the content of register 21 is available here. Okay. Because once you specify that inside your RR2, that content will be automatically available in RD2. But it's just that we are not using it because that is not the intention. The intention is for 21 to be specified as the write register, not read register. So even though it is available, we are going to ignore it. We're not going to use it. Okay, but in this case, we are not going to use it because that is the data that I want to write to. So in this instruction, I'm taking this data and I'm going to write into this address. So the address is again, as just now, the content of register 22 add with negative 50. So negative 50 is the one that will be selected through this multiplexer here. All right, and here I will again do the add operation and I'll get the address. So this address is what I'm going to specify over here. Okay, and since this is a Stalwart instruction, your mem write will be activated and together with the data from register 21. So the data in register 21 will be connected here. Okay, and with mem write activated, I will then update the data. So in Stalwart instruction, I'm not reading data from the memory. I'm not interested in taking the ALU result and channeling it back. So there is no write operation involved. Okay, so these are the two things. Let me check. Yeah, so just now I talked about instructions. Yeah, it's about the MIPS instructions. All right, so I think that's basically the whole data part. Okay, and we also covered the whole idea of control signals as well. Okay, so basically you can see that the control signals, we will also rely on them to channel the data correctly. For load word, how does, so as a question, for load word, how does WD have the register 21. Okay, so for load word instruction, the 21 here is the register specified in RT, correct? And that is mapped to here and also here. So the register destination control signal will use the multiplexer to say that register 21 will be selected to go through and specify as the right register. Okay, because this multiplexer has two possible inputs, either the RT bits or the RD bits. But here there is no RD, correct? Because it is a I-type instruction. Okay, so the whole idea of control signals, all right, for now, how you can take it is that the correct control signal will be activated when you want to channel any data through to the next stage. Okay, so what you need to know is, okay, what is the data I'm interested in, or what are the bits I'm interested in, depending on the instruction I'm trying to execute. All right, so let me come back to our notes here. Okay, so if you take the I-type, okay, so if you take I-type instruction, for example, as a R-type instruction, in this case, this is RS, this is RT, this is RD. Okay, so this is RS, so this is 9, and this is 10, and this is 8. All right, so for this instruction, we know that the register I'm supposed to write back to is register 8, which is this. Okay, and the bits or the where I need to specify the register I want to write back to is here, the WR, the right register. Okay, so I need to make sure that the 5 bits here, or the bits that come here, also say 8. Right? Because the instruction, okay, according to this instruction, the right register, or the register I'm supposed to write back to, is register 8. So 8 must come here to WR. How can I make 8 come here? All right, so I need to look back at the instruction. And in the instruction, this 8 is mapped to the bits 15 to 11. So which is coming in here. All right, so I need to make sure that these bits are the ones that are selected to go through. Okay, so coming back here, if I look at load word instruction, again this is RS, again this is RT. Okay, and this is the register I want to write back to. That means the WR, this location here, should have the value of 21. So where is 21? So when I look at this instruction, RS comes here, 21 comes here. Correct? So, and since 21 is also connected here, this register destination must make sure that the 21 is the one that is selected to come here. All right, so the idea of the multiplexer is it must choose the correct data, okay, to channel to the next stage or the next part of the processor. All right, what is correct depends on the instruction. If it was a R-type instruction, then I want the bits from 15 to 11. Okay, if not, in this case, I-type instruction is 20 to 16. Okay, these control signals are not stored anywhere. These are bits that are generated from the instruction using the opcode, okay, and the function field. Okay, so using this opcode and using this function field, I will be able to generate the correct control signals. Okay, so that is actually the next set of slides. All right, so I already uploaded the slides, okay, but we will go through that in the next lecture. Okay, so the bits as long as you know which bits you are referring to, is fine. So for example, RS, we say is 25 to 21. Okay, RT is 20 to 16. So it is from the most significant bit down to the least significant bit. So all this numbering is from the most significant down to least significant. Okay, so of course the whole instruction is 32 bits, but in this case we are extracting out. Okay, we're extracting out just specific bits for the different parts of the instruction. Yeah, the control signals are all the signals in purple. Okay, but I think it's not very clear here. Maybe on your slides, it might be clearer. Okay, so all these purple words over here, these are all the control signals. Okay, any other questions? All right, I'm sure you will have more questions and more things to ask after you go through the material one more time. All right, if you are still not sure of certain things, do not be worried. Okay, it is quite normal. Okay, especially for the first time looking through all of this, to be a bit overwhelmed and trying to figure things out and on what is happening. All right, so it's okay. Take some time to absorb and digest the information first. All right, and then we will see step by step what to do. All right, so next week is the recess week. Okay, so there is no class for next week. Okay, and so I'll meet you all again after next week. Okay, where we will finish up with the control signal and we will do the next tutorial 3. All right, so I will still be here on the call for those who want to ask questions. For those who are done, all right, you can log off. Okay, I will answer whatever questions you still have on the chat. Okay, so there's a question to go to the last green line you draw in notebook. Okay, so let me go back here. Okay, so this last green line over here, this is basically after you read data. After you read data, okay, you actually have one more multiplexer, which you can see from this slide over here. Okay, so why we have one more multiplexer here is because, okay, this multiplexer is to differentiate between the two sets of data that is coming through. Okay, it means either data that is coming from the memory or the data coming from the ALU. All right, why? Because if it was a load word instruction, then what you're interested in is the data coming through from the memory. If it was just an ALU, I mean, it's just an R type instruction like this, then the data you're interested in is the data that is just coming out from the ALU itself, nothing to do with the memory. All right, so that is why you can see that there are two possible options. One is from the ALU, the other is from the memory. Okay, so that is actually what I drew over here. Okay, so actually there's another line over here which is from the ALU. Okay, but for the load word instruction, we are not interested in that. What we are interested in is the data is coming out of the memory to be channeled back to the processor. And how is it channeled back? It is connected to the write data pins of your register file. And your instruction already specify the write register as 21. Okay, so that is this. Yeah, the write data in data memory writes it to the address that you specify. So your question is, the write register shares the same address with write data. Yeah, so the write register, okay, so if you look here and you look at this, the write register, okay, and write data are still specified by the same bits, which is 20 to 16 over here. Okay. Only thing is over here. Okay, over here you are saying that this is the register you want to write back to. Okay, so that is why over here we are actually taking 21 to come to the right register. Whereas in the Stalwart instruction, this register 21 is actually here, going to RD22, which will then be written to the memory.
So in the Stalwart, for this Stalwart one, right? When we put in register 21 into WR, actually later on we don't use that already, right?
Yeah, we specify register 21 as the data that we want to update into a particular memory.
I see, correct. Because you want to store the information in, you want to store the information in the 22 offset by 50 into 21, right?
No, we want is the other way around. Take the data in 21 and store into the address specified by 22 minus 50.
I see. Then in the right in the register file, because we haven't calculated the address yet, right? That will be done in the ALU. We haven't calculated the destination address.
Yes. So the data is already available from the register file, but the address will only be available over here.
I see. Then why must we specify the write register in register file if we are not going to write to there eventually?
No, so we are not using it at all. So this is again hardwired. We are not explicitly doing it.
There's no way to leave it blank, the WR.
No, so it won't be blank. There'll be something there, but it makes no difference because we will not activate register, right?
That's right, because Stalwart, the storing of the word will be done in the data memory area, right?
Yes. So in this case, the write register will have some data there. Write data will also have some data there, but it does not affect anything because the register write control signals will not be activated.
I see. So there will not be the green line such as the load word. Just now the green line that Ichun was mentioning, we will not have that in Stalwart.
Yes.
Okay. Okay, thank you. Yeah, quite complicated.
Yeah, it takes a while to relate to all the different instructions and see how everything comes together.
Yeah, and there's so many redundancies which makes it a bit more confusing also.
Yes. Yeah. But I think not to be worried. When we go through the tutorial questions, I think then you will get a better idea of how everything comes together.
Okay, thank you, Prof.
Okay, so I think that's all for today. We went the full 3 hours. It's 9:30. Okay, so thank you very much. So next week, anyway, after I upload, I will also send an announcement to update everybody. Okay, so next week is a break, and then I will see you all after that.
Good night.
Okay, so thank you. Good night.